do it today or tomorrow. And then that's the last one. It's on state space. And after that, your final exam will be due to the content for today. That's it. So everything up to from second order systems to state feedback control will be on the final exam. Final exam, same format as the midterm. 4 questions you just answer for. You're allowed to bring in 2 pieces of A4 formula sheet. So you reuse your midterm one, that's your 1 sheet, and then you can add on for your final 2. Yes? 2 A4 front and back.
So 4 pages.
Yes. So you reuse your midterm one, so you don't need to redo up. I hope you didn't delete them or throw away up. So you have to do again. So you reuse 1 sheet from your midterm, then you're given 1 new sheet, both sides, for the second half. And you can put whatever you want. Yes?
But the content is mostly focusing on the second half.
Of course. I'm sure you realize there's a lot of the second half really got more than enough. But the thing is, you cannot forget Laplace transform. Like you can say, you need to know Laplace transform. You still need it. But the content will be focused on the second half.
You will be providing like the transform tables and etc.
Same as midterm. Same as midterm. Yeah. Okay, and then this week, for tomorrow, as well as Thursday, your lab session will be the full state feedback control of the inverter pendulum. Please come to it. It's very magical. At the end, you'll see the pendulum stabilize in front of your eyes after you devise the full state feedback controller for the system. Okay, so we'll do that. The lab worksheet is already out. So tomorrow you will need to bring the M file that you did for the lab, as well as download the lab view file for tomorrow, which you have. So today we will continue and finish up the full state feedback control. So here I have a nice summary. So any state space system, right, you can always express it in this form. The A, B, C, D. Any LTI state space system can always be expressed by this A, B, C, D state space system. The characteristic equation for this state space system will be the SI minus A. You find the determinant, you get a polynomial S. You can read it in this form, right? That means the system and the poles of this system. So maybe for those who forgotten the poles. So the poles for this system will be S equals to minus P1, minus P2, all the way to Pn. Okay? So this is for the open system. Means you don't put any control, you just analyze it. The system will have this characteristic. Then yesterday we went through how to introduce control for state space system. And very simple, it's full state feedback control, and the control law that we use is just U equals minus K. That's all you need to remember. U is equal to minus Kx, where X is the state vector. So K will have the same number of elements as the number of states, which is also the number of states also corresponds to the order of the system. So you have 4th order system, you have 4 states, that means K also has 4K, K1, K2, K3, K4. So once you know the control law, which U equals Kx, you can substitute into the original state space system, simplify, you will get x dot equals to A minus Bx, Bk times x, which can be written as an A bar x. So once you substitute the control law, it will reduce back down to another state space system. Okay? There's a state space system for closed loop. It's also, despite that it's a closed loop control, the expression for the system is still a state space system. Okay? And because of that, if you want to find the CE for this closed loop system, that will be SI minus A bar, right, which is also equals to SI minus A plus BK. Okay. So this is the closed loop characteristic equation. This is the open loop characteristic equation. Right, so you can see here, with K, which you are free to adjust, you can change the closed loop poles. Right? So for control design in state space, right, there are 3 steps. Actually, there are actually 3 steps. First step is check. Second step is desired. Third step is compute. Okay, first step is you check whether it's possible. In this class, as I mentioned, it will always be possible. Okay? Just in case you find you cannot do it, you will see that when you try to compute k, you cannot find k to satisfy your requirement. Okay, step 2 is you need to know the desired performance of the system. Right, so this will be given in the problem. It will tell you you want the system to the closed loop force to be at -2, -1, for example, that's one. The other way is you can set it by setting the desired performance specification. You can say, oh, I want the system to have a time constant of so and so forth. Or you want the system to be 5 times faster. All this will tell you where the desired flow will be. That's step 2. And then step 3 is to compute k. And all you need to do there is just need to compare, equate the desired accuracy equation with this expression here, the SI minus A plus BK. And once you equate these two, you'll find that everything is known except K1, K2, all this is Kn. And that's what you compute again. So we did an example here. We did this very simple example, first order system, right? And the first thing was to check the CE of the overflow system, which is SI minus A determined. And we found that the CE is S plus 1 equals 0. So that means this is the first order system. There's one pole and the pole is at -1. So this is a perfectly nice and stable system. Right? What's the time constant? Because this first order, you can find the time constant, and remember the pole location reciprocal is the time constant. Because one reciprocal is q1, that means the system time constant is 1. Right? So then the next question is, we want to now implement a controller such that the system is 5 times faster. So 5 times faster means your time constant needs to be 5 times smaller. So now the time constant for the open system is 0. If you want it to be 5 times faster, the desired time constant for your system should be 5 times smaller, which is 2. Right? Once you know the desired time constant, you can compute the desired pole location, which is S equals -5. Okay? So with this, you have the desired CE of your system. If your system CE is this, you will have a system that's 5 times faster. So with this, you just compare to the SI minus A plus BK expression. Right? You just substitute in, you know A, you know B, and you just need to find K. And then you compute it out. You get here, you see S plus 1 plus K1 equals 0. You get this equation to this. And the only way for this to occur is when K1 is 4. Right? And if I rewrite the control law, so U is equal to minus Kx. Right? So the control law is minus 4x. So that means you read x, multiply by 4, put a minus sign, substitute back to the system, and the system will give you a system that's 5 times faster. Okay? So this is a first order example. Let's do something a bit more challenging. Let's now look into a second order example. Why is it the second order system? There are a few ways to look. First thing is you look at the dimension of the A matrix. This is a 2 by 2 matrix, right? You see here, this is a 2 by 2. That means the n for Norway, is 2. Right? Okay, so first step is we do something easy. Compute the poles or eigenvalues and CE of the overflow system. Maybe you tell me the answer is here. If you want to find the CE of the overflow system, SI minus A, find the determinant. Why don't you try? Find the CE. So once you have the CE, when you solve the CE, you can find the poles of the system. Why don't you do it? So calculate SI minus A, then compute the determinant. Again, the A is the 0, 1, -1, -2 matrix. Maybe I have time we can do together. Okay, so to find the CE, it's SI minus A, working determinant. So this is S00 S minus A. A is 0, 1, -1, -2. Right? And then, so 2 by 2 minus 2 by 2, you just continue what you need to do. Right? Yeah. So this one S -1, 1 was 0 minus -1. And S minus -2 is S plus 2. And now you find the determinant of 2 by 2. So determinant 2 by 2 is this times this minus this times this, which will give you s plus 2 plus 1. And then I will expand it out, I get s squared plus 2s plus 1. So this one very nice. I can factor out s plus 1, s plus 1. Okay, so this is the CE for the open loop system. So everything makes sense because the second order system, I have 2 poles here, plus the highest power is s squared. So maybe you all can tell me what are the poles of the system? So the poles, just to make sure everybody is aware, the poles are at s equals to minus 1, minus 1. Okay, so anybody can tell me this system, can you use some words to help me describe the system, knowing that this is
Stable.
stable, very good. Anything more? So this is the second order system. No, so the keyword here is they have repeated real poles. And once you have that right, there's only one outcome. That means the system is critically dead. The damping ratio is exactly 1. Damping ratio is exactly 1. If you're wondering, how in the world do you know that? You can. My suggestion is you compare this to the standard form. Okay, so in this case, omega n squared equals to 1, omega n is 1. And the only way this equation will make sense is when zeta is 1. Then you get the 2 there. Right? So actually, if you write this thing out, you will also know the system. You already know that it's critically dead, so zeta is 1. If you write out the standard form, you also know that the natural frequency of the system, omega n, is 1 radians per second. Right? So that's good, right? We are doing detectives, we know now the system second order is stable, critically damped. So this system, right, if you were to put a non-zero initial condition or you put a unit step input, the response side will have no overshoot. The rate is critically damped. Okay. So far, okay? Okay, good. So we can go on. So we already established this, eigenvalues this. Okay? Then we can go on to, the goal here is to design a full state feedback controller such that for this second order system, such that the desired poles, this system should operate at -2 plus -2 minus square root 2j. So I'm sure you realize that the system is not bad right now. The system poles are -1, -1. But then I want the system to operate at where the poles are at -2 plus -2 minus 2j. Okay, so with this information, we can construct the desired characteristic equation because we know where the 2 poles location should be. Right? So how to convert that information into a CE? Anybody can suggest? So right now, I will write in terms of variables. Maybe then they help you with terms. So right now, I will, for the desired poles, we have the desired poles to be S equals to, I make it generic first. I tell you there's a minus Q1 and minus Q2. Don't put the S on purpose. Okay. So let's say if you want the system to have 2 poles and then they are located at Q1 and Q2, can you convert this into a CE for me? So right now this is not CE. So yes, I heard something like, so actually if you put it in S plus Q1, S plus Q2, this equation, when you solve for S, you get the first 2. You get S equals to minus Q1, S plus Q2. So that means this CE will describe these 2 poles then. So then here you can expand out S squared plus 2Q, not Q. So here is Q1 plus Q2, S plus Q1, Q2. Right? And this is the C. Agree? So now we just need to substitute what we have. Now we have Q1, Q2. Sorry, I'll do it later. So now what we have instead is minus 2 plus 2 square root 2j. Right? And the other one, this is where you must be very careful. This is the conjugate. Right? So when you're finding out what to do now, so let's give it more space. So I rewrite this, it's actually s plus 2 minus 2 square root 2j. And it is s plus 2 plus 2 square root 2. Looks scary, right? But when you expand out, the conjugate will disappear. Because you're multiplying conjugate test. Okay, so when you expand it out, you will get this s squared plus 4s plus 12. When you multiply out, the conjugates will cancel. Whenever you find that your CE has an imaginary part, right, something wrong. You did something wrong. Your CE can never have a J inside. If you encounter a CE with J inside, please look at it. It's impossible. Impossible. So don't try to continue and think that it's okay. Yes, is a question? I haven't reached there yet. So everybody okay with the constructing the desired CE? So because the previous example was, I tell you it's 5 length faster. Then you read it. Here is, I tell you where I want it to be. Already. You just need to convert the whole location into a CE point. Equation. Yeah, so this is we want the system to have this CE for closed loop. So the next thing is we need to find the system CE in closed loop full static black. And this is where we need to know what's the K. So I think someone was asking. So this is a second order system, so your K is K1 and K2, which is written there. And then if you follow the same analysis from here, here. So you know the A, you know the B, and the K is K1, K2. Right? From here, you just put it in. So this is S, this is S times I, this is A, B, K. So I want you to know that this appears very strange, it's correct. So maybe I just go through that part, that multiplication part. But some of you might be wondering, how the one looks wrong. Okay, there's this part here where you have K, where B multiplies K. Right? So there's this part here, B times K. Right, so this part is actually, so your B is actually 0, 1 multiplied by K1, K2. Okay? A few of you might think, hey, something is wrong. Doesn't look like I can multiply, but it's actually correct. Because you can do this times this, becomes 0, this times this, 0. 1 times K1 is K1, and this is K2. And you can, because the inner dimensions agree. So this is actually a 2 by 1. This is a 1 by 2. So the inner dimensions match. Inner dimensions match, then the outcome becomes 2 by 2. This is a 2 by 2. So makes sense, huh? So you have the SI, this A is 2 by 2, then B times K is 2 by 2. You add together, you get to this. Once you get this expression, you find the determinant. This times this minus this, you get to this expression here. Right? So now we have two equations that are supposed to match each other. We have the closed loop CE, which is here, and the desired CE, which is here. So this is the easy part. Once you have these two equations, the last step is you equate the coefficients. Right? For these two to be equal, 12 must be equal to 1 plus K1. Right? That means K1 is 11. And then the other one's 4, because 2 plus K2, that means K2 is 2. To rewrite then, you'll find that this is the 2 numbers here. You can rewrite your controller, so K is 11, 2. And then your controller, basically just 11, 2 multiplied by T1, X1, X2. And the system will have that performance minus 2 plus minus 2 square root 2j. So you can see that for state feedback controller, it's very methodical. If you follow the steps, very difficult to go wrong unless you make a computation error. Okay, you'll be surprised. I mean, that's what you say. You promise me, and that means in the exam, oh, you'll get more, right? That's the same. Yes. Okay, in this class, for your first class to review, it's possible to be angry but not inspired. Yeah, so I think most of you can get this concept. The main source of error, right, is careless mistake. You equate wrongly, you compute wrongly. That's normally the main source of error. Right? Or I tell you the main source of error. When you compute the eigenvalue side is wrong. That's a very major mistake. So once you compute the eigenvalue wrong, it's always have a snowballing effect. And it could be maybe you compute the determinant wrongly, things like this. So keep this in mind. But any questions? So we did a first order example, a second order example. Let's do a more advanced example. So this one is one exclamation mark. We try another example with, let me show you the graph. So the green one is the overload system. So the system with minus 1, minus 1. You can see that this is system right, critically damped, right? Now with the red color one, which is now operating with 2 poles with complex part, you will see that now it will overshoot. Because now the damping ratio of the system is less than 1. You can also see that the system is faster. Why is the system faster? Because previously the system was minus 1, minus 1. Now you go to minus 2. So it's like almost twice as fast. Okay. So again, green color is the system without control. Red color is the system response after you add in the full state feedback control of the gain 11.2. This system here. So okay, next then let's go on to a newer example here. So here I have another example. I will erase a lot first. Okay, so here we have a simple pendulum system, not inverted, so very simple pendulum system, where the pendulum angle is described by theta, right? So going counterclockwise is theta, right? And then there's the mass at the end of this pendulum, which will cause it to go back. And then U is the applied torque. So that's the input to the system. You apply this torque, which is going counterclockwise. Okay, so you can see U is the input torque. And it says the output will be the angular position theta. So that's the key word. So when you derive the state space system, you should do the Y should give you position, angular position. Okay, so to make life easier for you, I let L n equals to 1. And then there's no friction from the air. So we did this in a vacuum chamber. First thing first is we need to find the equation of motion. Then we derive. Okay, so this system, if you were to derive the equation of motion, which I think we've done before, this is the equation. So you take moments about the pivot, sum of the moments, is equal to J times the theta double dot, which is the angular acceleration. Right hand side is the sum of all the torques applied. So there is applied by U, and the other is due to the pendulum mass, NGL sine theta. So this, I hope you realize, is a non-linear equation motion because of sine theta. Right? Sine. Whenever you see trigonometric functions, they're not your friend. It becomes a non-linear system. So here what we need to do is we need to linearize this equation motion. Anybody got any suggestions on how we can linearize a system like this easily? Small angle approximation, right? So but before I do this, I'm going to rearrange this equation. I will J for this system is ml squared, right? I will divide it such that the left hand side has no more ml squared. So you get. Okay? So this is a second order system, right? So second order system, so if you were to express this in space, we will need two states. So keep that in mind, but before we do so, we need to resolve this sine theta. Okay, so right now we're going to do small angle approximation about theta equals 0. So sine theta, when theta is small, is approximately theta, right? Cos or small angle. So when theta is small, sine theta is approximately equals theta. So from here you can do this linearization. You can hear. From here to here is noting that L and M are 1. Okay? So L, the length is 1, the mass is 1, everything, so you get together. G is 10. If you don't need to put 9, yes?
How do you know whether to do small angle to linearize or to do operating point to linearize?
So once you have an angle system, normally the best way is to do small angle approximation. Here, the small angle approximation is about 0. It's quite different from the inverted pendulum where we put the pendulum up at pi. Here it's actually looping down. So the operating point is actually 0. Yeah. It would not make sense for you to linearize about pi because we are not doing inverted pendulum, we're doing a normal pendulum. Okay, so then we go from a non-linear equation of motion, and then we linearize with a small angle approximation. That means sine theta is roughly theta. And do you agree, is this a linear equation?
Yes.
In this form, can you write it into state space expression? Can you? In this equation directly, can you go into state space? Why? What's wrong? Okay, your left hand side has 2 dots. Okay, right hand side no dot. Remember, state space is left hand side 1 dot. Right hand side and no dots. So again, recall that this is a second order system. We actually need 2 states. We haven't drawn any state definition yet. So we should start with the simple state definition. The easiest is to assume x1 to be theta. And then x2 will be theta dot. Okay, so that's normally the first state definition, right? x1 is theta, x2 is theta dot. So with that, you will have, once you define that, right? Okay, so that means x1 is theta, and x2 is theta dot, which is equal to x1 dot, right? So I rewrite this guy, it becomes x1 dot equals x2. It's nice, right? Because this is left side of dot, right side of dot. So what's missing here? I have one of them, I need one more equation. Where can I get the other equation? Yeah, so we haven't used the equation of motion yet. So I'm going to write down the equation of motion. So equation of motion is different color, so you can see. So equation of motion theta double dot equals to minus 10 theta plus u. Okay, theta double dot is x2 dot. Minus 10 theta is x1 plus u. So I'm going to box for you the 2 equations that I really need. 1. With these 2 equations, can you express it into state space form and derive the A, B, C, D? Okay? Okay, fine. Tell me what's A, B, C, D. Wow, you can do it in your head. So excellent. Okay, so let me see which color I should use. Green. So I need something like this, right? X dot equals to AX plus BU. Okay, I will write the A this way. Good. Okay, so this is x1 dot plus x2 dot. I can use a different color. So x1 dot is x2, 0, 1, very good. So very good. 0, 1. Then any u? How about x2 dot? Negative 10, 0. Okay, let's also complete the thing. We also need the c and d. So y is cx plus du. So can you tell me I said you see the output should be the angular position only. So what should it be? This one angular position. Angular position is this guy. So I just need which state do I need? X1, right? So in order for me to pull X1, so 1, 0, and this should be no 0. State this form is here. Right, so you have the A, B, C, and D. D is 0. So this is the state space representation of this in this simple pendulum system. And so I don't think the question asked, but I just want to ask you for your thoughts. If you want to find the poles of the system, what do you find the poles of the system? So you find the eigenvalues of the A matrix, which is the 0, 1, minus 10, 0. So I'll leave it as an example for you to test it out. Before you do so, I want you to think about it. If you were to compute the poles without you computing, if you look, imagine the system, can you tell me something about the poles? Maybe something is simple. Is it going to be stable? So you think about it, you let this pendulum go, there's no friction, and you keep going. So let you think about it. You go and complete the poles, and then you will see whether what you think is correct. I won't tell you the answer, I want you to think about it. So the answer is very simple. You just find the eigenvalues of A. The pole location will tell you whether the system is overdamped, undamped, stable, unstable. I'll let you figure out. I just want you to think about imagining system, and then think about what you expect and what you consider. Hopefully it's the same. Anyway, I'll let you think about that. Okay? So now we go on to the last part, which is the most important part. We want to design the state feedback controller such that the closed loop poles are at -1, -2. Okay? So I will clean up this page and get to here. Right? We will do state feedback controller. This is the second order system, so you have K1 and K2 again as before. Right? So again, the first thing from here we need to compute is the desired CE. Can you tell me what's the desired CE? So the hint in the question already tells you where to place the pole. But telling you where the pole is not enough to give you the CE. So you need to convert that into the CE. Anybody can tell me what is the CE? So it's S plus 1 times S plus 2. Do you agree? So that when you solve this equation, you get S equals -1, S equals -2. What? I mean, the question didn't ask for it. Yeah? You don't actually need to know that, right?
You need to know.
Okay, so you have the desired CE to be S plus 1 times S plus 2. You expand out, get S squared plus 3S plus 2 equals 0. So this is the desired CE. And now what you need to do is to compare the coefficients to the closed loop CE of the system under full state feedback control. This expression will have the K1 and K2, and as we've done it before here, do the same thing here. Si minus A plus BK, multiply, you get to here. You will get a same ordered polynomial in S squared, like this form. So from here, this is the last step, easiest step. We just compare this equation with this. Can you tell me, let's do the easy one. What should K2 be? 3. K2 should be 3. Then what should K1 be? Negative 8. So this example is to tell you the gain can be negative, but it doesn't mean all gains must be positive. It is possible that we have a negative gain. Okay. So negative gain actually means actually slowing down the system. Okay, you want to know. Okay, so then the system K is this. And if you want to employ this controller, it's very simple. You read the state x1, x2, multiply by this, and that's the controller. Sort of. Sort of. Even at this point, K1, K2, right? K can also, the K1, K2 can also be 0. That means don't change the response. So imagine here, you find the occlusive poles, right? And I suggest you try this again. You try to set the system to operate at the same pole. Then find K. You'll find that K1, K2 is 0. Because you're already at the performance, there's no need to change this here. Sorry? Just to give you a sense. Just to let you know, if you were to try to design the system to operate at where you are, you'll find that K will be 0. Sometimes the K, not all of them can be 0. It's possible that you'll find a system where it becomes minus 8, 0. Nothing wrong with that. That means once the state, right, the performance is correct, and nothing to change. You can think of this as the K1, K2 is a gain correspond to one of the states. So K1 operates with x1, K2 operates with x2. And remember, x1 is angular position, x2 is angular velocity. So you have two gains here, one operating with velocity, x2, K2, one operating with the position, which is K1, x1. Yeah. You can think of this, I don't know whether somebody will catch it, it's like a PD controller. We have position feedback and velocity feedback. Similar, not exactly the same, but it has the same performance. Okay? So far, okay, you can see here it's very methodical. You follow these steps, you cannot go wrong. The only way you can go wrong is you make a calculation error, guaranteed. Yeah. So I'm very sure all of you can do it. It's just that I think maybe during exam time you stress yourself and then you calculate, you write down something, maybe you write 10, become 16, very common mistake, and the error also. Everybody okay? In this second example. Yeah, so I summarize, you first find the desired CE, find the closed loop CE, match the coefficients for K1, K2, or whatever K3. And that's the controller again. Yes, but it's not called PID, it's still called state feedback control. Take 114. Take 114.
Well, what you mean by it's same as velocity and position in a PD control?
Yeah, so x1, x2 is position and velocity. So K1, K2 is, you can think of it as proportional gain, velocity gain. It's somewhat related.
So technically you use the state space to adjust your PID stuff.
Yeah, that's why I said I don't want you to think of it. It's not. The PID is meant for single input, single output system. Here, this system, right, there are two states. You're reading the two states at one time. Yeah. Yeah. So this system, if you want, you can design a PID controller. You can doing the normal way. So that means you find the transfer function. You can derive a PID controller. It's slightly different. The gains will be slightly different. So this is called state feedback control. Controller of U equals minus Px. Okay. You must use it in this form. So on Wednesday and Thursday, we will use this form to control and stabilize the inverted pendulum. So you just need K1, K2, K3, K4. So Wednesday and Thursday. As a last example for today, right, and also this class, we'll do a third order. Just to show you that no matter how complex the system works, the fundamental approach, right, is the same. Is the same. So here I have a third order system. how to know it's third order. A matrix is a beautiful 3 by 3. It's a beautiful 3 by 3. And it says here, you want to design a state space controller K, and the desired poles are listed here. So there are 3 desired pole locations. Want to find K's in this system, reach there. So again, the first thing is always to find the desired CE. Right? So from the desired pole location, you can always rewrite an equation that describes this CE, desired CE. So you expand it out, you will get a cubic polynomial, s cubed plus 14s squared plus 60s plus 200. Okay? Yeah, so again, you have 3 desired pole locations. These 3 desired pole locations convert into a desired CE, a third order CE. S cubed plus 14s squared plus 60s plus 200. Once you get to here, same thing as before. You write out Si minus bk, Si minus a plus bk. Okay, here, you write out this thing. Right? Expand out. You get a 3 by 3, and here you compute the 3 by 3 determinant. So you can use my visual trick, compute it, you simplify, you get this expression here. Same as before, you will then compare this with this desired CE. And from here you can see that 6 plus K3 should be 14, 5 plus K2 is 60, 1 plus K1 is 200. Okay, and then you have 3 equations, 3 unknowns, you solve for K1, K2, K3. Then you can solve that K is 199, 55. Okay, so this is the order. Then tomorrow, or Thursday, you will do the 4th order, right? Because the dividend pendulum is a 4th order system. So the good thing is, you don't need to compute this. MATLAB can help you compute this for you. Okay. But the fundamental approach is the same. First order, second order, whatever. You can see the state space, right? It doesn't matter how high order, the approach is the same. That's the beauty of this system. So any questions? Because with this, we are done for state feedback control. So the final exam, right, will only cover up to today. Any other questions? If not, Henry? Yes. I mean, it's from second order system onwards, because the midterm is up to first order system, right? So your exam, your final exam will focus more from second order system onwards. I cannot say the 5 parts not tested because I still need you to know the part transform. I cannot say you forget that, right? But the content will be focused on the second half. Okay, so final value theorem, we still need you to know. Laplace transform, you need to know. Inverse Laplace transform, you need to know. Okay, modeling, somewhat you still need to know a little bit, but that's not the focus. You still need to go through like liquid level modeling, thermal modeling, linearization. We also cover system stability, system types, Bode diagram, good Lucas. We won't focus too much on the Fourier series, Fourier transform, all this we tested you already. If I tested you before, I'm not going to test you again. Because there are so many other things to test. You can bet your life, one of the questions is state space. You spend 2 weeks on this. I'm sure you can bet your life, you will see a state space or one of them. Guaranteed is state space, right? You cannot run away from this. But as you can see, this is very structured. If you know what you're doing, it's a free one question. You will definitely get all the things right. Okay, so let me summarize what we have done. Right, so we have done state feedback control. We have actually focused on regulator system. So regulator system is when the reference input right is not moving, not changing. 0 is actually one example of not moving. You can actually expand this to control system. Control system is when the reference input is time varying. For example, ramp function, sine function. This will be control. Right? So I think we talk about, we don't really focus too much on where to place the pole. Just telling you that if you know where to place the pole, you can find K. If you are interested to know where is the best location to place the pole, we have this thing called quadratic optimal control. Right? The best place to place the pole. we won't cover this class, but you're interested, we'll cover this in 3114. So it's actually the best controller, right? Best controller for that. Alright, so again, this K, back to the same thing we talked about for state space. Because for any system, we'll come back to here. You know this pendulum system, right? This is not this expression here is not the only state space representation of this system. Because this is not the only state space representation of the system, the gain K is also not unique. The gain K that you compute is specific for that state space. So if you were to create a new state space expression which describes the same system, you compute the K for that system, that K will be different from this K. It's not to say you're wrong and right, or different state space systems have different K, but it will still be correct. Okay, so that's the thing I wanted to mention for that. Right, and then if your system is high order, like the inverted pendulum, you will need to do some testing, trial and error to change the gain K. So on Wednesday and Thursday, you will try to change tune the controller gains K1, K2, K3, K4, or the inverted pendulum. So that's a good example of a high order system. And then, so with this side, and I don't have to mention because some of you are somewhat interested in 3114. But you're wondering what you're going to cover in class. So we actually will go into state space in greater detail, like significantly greater detail. We'll cover things like optimal control, things like that. We also spend half of the semester on digital control. That means if you were to implement your controller on a computer, it's very different from implementing on computer side. Because your computer is sampling. Actually, will spend time, right? We have a nice 1D and 3D project. 1D is the magnetic suspension, and this semester you do what we call continuous time control of inverted pendulum. In the 3114 you do digital control. Okay, and then the 3D is actually you assemble a drone, and then you implement an altitude controller onto the drone. That is 3114 in term 7. So still a lot of time for you to think. Yeah, 3D because it's linked to this class. Linked to this class. 3D means across semester. Yeah. 2D is within the same semester. 3D is across semester. So this 3D is linked with this class. 4D is what's 4D? What 4D I think is no. 4D is the outside classroom learning. Like your fifth row, your Wednesday, Friday. That's 1D. 1D is within the class, right? 1D project. 2D is across 2 semesters. Within the same semester, 2 classes. 3D is across different semester classes, and 4 is outside classes. I remember Friday, 1D, 2D, 3D, 4D. So that's what I have. I will provide you on next Monday. So this coming week, the content you need to do for your 2D. In the gist of it, right, I just need you to implement a feedback controller to maintain a temperature, specific temperature in one of the nodes. That's it. This controller can be any feedback controller you want. You can just put key controller and do PI, whatever, anything.